Hey everybody, welcome to another CS302 assignment video. This will be assignment 6 where we're going to, simulate this lunar lander type program. So it won't be a fun game like this, but just to give you an idea of how this game is actually played, there's actually a link right here in the PDF. So let's go ahead and let me go ahead and I'm going to go ahead and try to play this game. So the lunar lander is essentially trying to land this craft onto the moon. And of course, you have thrusters, as you can see right there, will allow you to control the speed of your lander. And you're trying to just land on the surface without crashing the actual lander is the goal of this game. So there we are. As you can see, we are moving towards the atmosphere, or towards the surface of the moon, sorry. So I think you get the idea. I'm going to go ahead and try to land this craft successfully. Okay, I think I'm doing pretty good. Okay, and okay, I think I'm not going too fast. Perfect, there we are. So I guess landed hard. I guess it wasn't a great land, but it was still good enough. And of course, if you let this thing just crash, if you just don't even control the speed, it will just crash and it will not exactly land successfully at all. Like right here, if I just don't do anything, this is a little scary. This is giving me anxiety just watching this, but that's okay. I feel bad right now. I don't want it to crash actually, but I kind of had to let that happen. So there we go. So if you land too quick, or you hit the surface too quick, your spacecraft, the lander, crashes. So anyway, so we're gonna be essentially simulating this program, except in our implementation of the lander class, we're not going to be able to change its direction. So it's going to be sort of moving downward direction only. You can activate the thrusters to control the speed by adjusting its flow rate and so forth. So anyway, let's go ahead and now just go into the actual classes to be implemented in more detail in this video. Okay, so here is the lander class that we're going to implement. So let's first look at the private fields of this class, and they're really self-explanatory. So we have a name, which will be the name of the lander of this aircraft. The flow rate is going to really be that thruster amount. So when I was simulating this game here on this using this link provided, you notice I was sometimes pushing up on the arrow keys to sort of ignite the thrusters so they would slow down the velocity of the fall of the lander. So the flow rate is going to be essentially the throttle, or how strong I'm going to sort of run the thrusters so to slow down the velocity in a downward direction. So essentially, flow rate will be any number between 0 and 1 and any decimal in between 0 and 1. Well, the velocity is going to be just the velocity either in the upward or downward direction. So the velocity is a positive number, it's moving up. If the velocity is negative, it's moving down towards the surface of the moon. The altitude will tell us its amount of meters away from the moon's surface. The fuel amount will be the amount of fuel we have in this spacecraft. Still landing is a boolean for true if it's still airborne, and false if it's crashed or landed. Lander mass will be the mass of the lander. Max fuel consumption rate, which means it's going to be how much fuel was burned when we actually ignite the thrusters. And max thrust will be the max number of thrusts this aircraft will be able to use. So we essentially set these in our constructor, and I believe I gave you the constructor in the lander.cpp file. And these getters are all self-explanatory: get velocity, get altitude, get fuel amount, get name. And now get status is a little bit, I guess, not so complicated, but the get status function, the way it works, it returns a character, A for airborne, which means still trying to land. It returns L if it's already landed, and it returns C if it's crashed. So the way you know if it's landed is that if the altitude is 0 or negative, of course, then set the altitude to 0 automatically. But if the altitude is 0, then that means, well, either it crashed or landed. So if the velocity is -2 or less, that means it's going to crash. It means it's heading towards the surface of the moon at a too fast of a rate, which means it will crash the lander. If it's less than -2, it's negative 1.5 meters per second squared, then it will be traveling at a slow enough velocity where it's not going to crash. So I believe I have this written down right here in the PDF. Now for a change flow rate function, this is going to be essentially past any R. That's going to tell it how much we're going to, it's going to be your throttle amount basically. So when I simulated the game a second ago, when I move up on the keyboard, that would sort of tell us how much thruster we're going to be using. So we pass a number between 0 and 1 inclusive, so it could contain 0 or 1 or any decimal in between 0 and 1. We pass it in and we update the landers, or we update the flow rate with this R parameter. Now, if the parameter is less than 0 or greater than 1, then we're not going to update it. So we return true if we're able to update, return false if we were not able to because the values were out of range. And also, before you return true or false, you want to check. So if, let's say, the fuel amount of the lander is 0, then you want to set the flow rate automatically to 0. So for example, if you have no more fuel left in the lander and you try to run the thrusters, it will not be able to. There's no fuel to burn. So before you return true or false, you want to make sure that if the flow rate is if the fuel amount is 0, then automatically set the flow rate to 0. Otherwise, whatever is in R, if R is between 0 and 1, you're going to set flow rate with whatever is in R. And then for the simulate function, you just calculate instantaneous velocity, and you just update your velocity field with V. I guess you're going to increment either by a positive or you're going to increment by a negative. So either way, you're going to update the velocity with whatever you compute here in V, update the altitude, determine if it's still landing or not, decrement the fuel amount, and then you want to set fuel amount to 0 if from step 5 the fuel amount does become negative, then make it 0, which means you can't have negative fuel. So those are given to you, very simple formulas to compute. And now we have this comparison operator we want to use. So we're going to actually store a set of landers in a priority queue. We want to determine which lander is in the lead. So being in the lead means which lander is closer to the moon's surface. So we want to use this operator so that way we can write our PriorityQ class to be very generic, so it can work for any type. And I'll explain a little bit later in the video as to what the benefit of this operator is. But really, this returns true if the left-hand side, that this object is smaller or closer to the surface of the moon. So essentially, we first check for the altitude. So we have the this object and a right-hand side object. If this object's altitude is smaller, return true, else return false. But now, if there's a tie, where let's say we're comparing two landers and they have the same altitude, then you want to go to our next tier. We want to check which one has less fuel. So if the left-hand side, that this object has less fuel than RHS, return true, else return false. But also, if it has the same fuel amount as well, we go to our next tier. We check for the larger mass. So if this object has a larger mass than RHS, return true, else return false. And then if, let's say, these first three tiers is a tie, then we're going to break the tie by just using the alphabetical order of the name. So essentially, if this object's name would come earlier in the alphabet than the right-hand side object's name, return true, else return false. So we have these 4 tiers. So whichever one, if there's no match, then we, of course, we use these to compute the higher priority. Returning true means the left-hand side has a higher priority than the right-hand side. So we're going to use that when we're bubbling up, bubbling down in our priority queue. So that's pretty much our lander class. Let's go ahead and now discuss the PriorityQ class next. Okay, so this PriorityQ class will be the same exact implementation like I went over in class earlier in the semester. So we use these header guards once again because, well, we might actually end up, how shall we say, redefining it in multiple areas. So to be safe, we'll put these header guards right here to end if, and we have the header guards right there. So like a standard priority queue, we're going to, well, we're going to have a key and priority value pair. So let's look at the struct. So we have a priority type, we have a key and priority. And I also gave you guys the constructor as well to make it a little bit easier to insert elements into the array. But anyway, you're going to have this heap array defined right here. It'll be of type priority type. So every element in a heap array will contain a key and priority value pair. We have the size field, which will tell us how many elements we currently have in a priority queue. Capacity will tell us the how many elements we allocated the heap array by. So our constructor, as you can see, we assign a capacity to value 5, size will be 0, and we allocate an array of size capacity, or 5 in this case. So that's going to be our essentially heap array. As always, it's going to be an array that really emulates a balanced binary tree, which is going to really be, it will maintain our priority queue. And of course, we're going to use a min heap. So the parent has to have a smaller priority than both children. So anyway, let's go ahead and go with the rest of the members of the class. We also have this map, item to PQ map, which I didn't mention in class. I also have these notes posted on my Canvas that goes over how this is going to be used. But remember, when we want to update a particular element in the heap array, this map is going to allow us to, in constant time, locate one of our landers, updates priority, and then bubble it up. So we don't have to linear search our heap array to find a particular lunar lander. So I already mentioned this in class, so of course you can refer back to your notes on that. So let's look at the public members next. So we have our destructor, which will be very simple. We only have a one-dimensional array, heap array, so we deallocate that. So this is very simple. You notice I didn't actually have us overload or implement the copy constructor or the assignment operator. And I guess it's because it's a very simple, it's so basic, there's no real benefit of that. So if, let's say you were to, let's say you write your main and you want to pass your priority queue object into a function, to avoid any issues, I would just say pass the object by reference, and then it's not going to invoke or call the assignment operator. So just pass your objects of priority queue type in main by reference to different functions to avoid any possible issues. So it's a very simple workaround. Okay, so then we have our pushback function, which is going to be our insert. So we insert to the back of our heap array. So again, in class, I typically used index 1 as the root, but in this implementation for yourself, if you want, you can use index 0 as the root. It's up to you, but I think using index 1 is a bit easier to maintain that. So I would just say use 1 as your root, but it's up to you what you want to do. But pushback inserts a new element of type, priority type, to the back of your heap array. And of course, size always tells you the back of the heap array. This is going to be the key field. It's going to be the priority field. Then you have to then call bubble up from that size position. It's the same code I essentially gave you in class. Pop front is going to be your delete. So remember, it's going to overwrite the root element with the last element in the queue and then bubble down from index 1 or from your root position. Now, also be careful whenever you do bubble up and bubble down, or whenever you push back or pop front, make sure that you update the item to PQ map accordingly, because you want to make sure everything's still consistent. As in, after you update the heap array, you want to make sure you update this map as well, so you know exactly where all of your landers are in the array. The update element, this is going to be a function where you pass in a key. It will find this element in your heap array, overwrites the priority value with this T2, and then it's going to either bubble up or bubble down. So in this lunar lander, imagine we have 10 of these landers. And what's going to happen is over time, as we simulate this game, we constantly update the throttle amount, which will cause the lander to either gain a positive velocity, so it's moving upward direction, or it could cause a negative velocity, which will move downward. So if let's say it moves downward, it might move up in the queue. So you want to bubble up in that case. But if let's say you update the priority value to a larger value, it might have to move down. So you have to bubble it down in your heap array. So just be mindful whenever you reassign the priority with this parameter, make sure you know whether you bubble up or bubble down. Then this function getElement will be used in main because when you have to update a lander, you want to pass in a lander name, and it's going to look up, it'll find that lander in your heap array, but of course using the items of PQ to avoid linear searching, it returns the priority field or that lander object back to you in main, because when you want to update the lander's flow rate, you want to update its, you want to call it simulate function, you have to return the object, return the lander object, update the flow rate, update, and then call simulate, and then you want to pass that lander into the update element function, which is going to reassign that lander's status, or landers, it'll reassign it to a new lander object, so it's going to have a new velocity, new altitude, and so forth, which of course will update in the queue as well. Then these two functions right here are just going to return the root element's key and root element's priority, so it'll return the lander object at the beginning of the heap array. And then this function is empty, returns true if it's empty and false if it's not. So if there's nothing actually, if your size is 0, it's empty. So actually, before I move on, you also have to overload or you have to implement bubble up and bubble down. Well, the same way we did it in class. So you have to constantly compare the parent's priority. If it's less than both children's priority, then everything is okay. But if the parent's priority is not less than either child, then you have to bubble down. And of course, for bubble up, same thing. You can always compare with the parent, and you always compare the priorities, and you want to always use the less than operator. So as you can see, in our example, T2 is going to be a lander type. So we're going to use that landers, because right here in our struct, the key will be a string, and T2 is going to be lander. And the priority will be the lander object, so we're going to use the lander object's less than operator to compare, to determine if the parent is less than the child, and so forth. So by using the operator, we're able to write this PriorityQ class to be generic, where it should be able to work for integers, but also it should be able to work for custom types as well. So as long as we overload the less than operator, it will work for any type. So that's why when we have to update our lander by reassigning the flow rate and reassigning the and then calling simulate, we don't want to update the flow rate and simulate within the PriorityQ class, because doing that, it makes your PriorityQ class it makes it specific for the lander types. You want to make it generic so it works for any type. So I don't want to ramble on any further, but that's going to be the overview of the PriorityQ class. Let's now go over the main and then the sample input and so forth. Okay, so for the contents of main, the first thing you will do is you can create an input file stream variable, and you can pass in this file name. So you'll be given a file that will contain your lander input. So you don't have to actually read this in from the user. You can just literally pass this string into the input file's open function, which will read from this file. And here's the file you'll be given right here. And I used AI to generate the names of the landers. I couldn't create creative names, but I think the AI created some pretty creative names, if you will. So here we are. So you're going to have, I guess, 10 landers in this program. And each line will be one lander object. So you can see that right here, give it to you. Each line contains a lander name, followed by the mass, followed by the max thrust, followed by the max fuel consumption rate, the altitude, and the fuel in that lander. So you read these elements in. It's going to be space separated, so very simple to parse it. So you can just use the extraction operator to just easily parse this. And you will take these fields, create a lander object, and you're going to push back or insert this into your priority queue. You're going to have a priority queue where the key will be a string, which will be the lander name, and the priority value will be the actual lander object. So inside of this object, that priority type contains a key and priority. The priority will be this lander. And inside of the object, inside of the priority queue object, you don't want to actually say something like heap array index I dot priority dot get altitude or dot get velocity. If you do that, it's too specific for the lander types. There's no point to even create a template because you could just use no templates for this. So you want to make sure it's generic where imagine that priority. So inside of your let me just go here and show you again. So imagine the priority type. You don't know what this value is. It could be int. T2 could be an int, but it could be a lander. So you want to make sure that it works for both. So inside of this object priority queue, inside the class scope, when you're comparing a parent to a child, always use that less than operator, not using priority dot get velocity or get altitude, because then it's too specific. It will obviously not work for integers. So just again, I mentioned earlier, but I want to mention it again if in case in my earlier segment in the video, if I talked for way too long and I bored you, then I want to make sure I said it again. So that way it's open now. Okay. So you read each one and you insert one by one into your priority queue. Obviously, you have 10 elements. So as you insert, you will have to resize your heap array. But I mean, I think resizing a one-dimensional array should not be difficult at all. So you may have to do a resize because the constructor given to you is going to set the capacity to 5. So after your 5th insert, the 6th insertion will definitely cause a resize to happen. You double the capacity at that point. So pretty easy. Okay, and then the next thing you want to do is you want to simulate this game, I suppose. So in our simulation, the first thing we'll do is this paragraph is going to be our simulation. We first want to output the top 3 landers, so the one that's in first place, which is closest to the ground, second place, and third place. Now, here's the thing about priority queues. All we can guarantee is that the root element is the closest to the ground. So you have to pop it off of the queue, put it into an array of some sort, pop the queue again, put it into an array, and then pop the queue again. So what will happen if you pop the queue 3 times and you store those 3 into an array, then you will get a sorted list where the first element popped off will be the first place, the next one popped off as second place, and the next one popped off as third place. You output those 3, then you have to push them back. You got to push all 3 of those landers back into your priority queue, so that way you can, of course, now perform your simulation. So in a simulation, you can imagine you're going to read from your standard input from CN, reading a string and a throttle amount. So what you're going to do is, well, let me just sort of show you what's going to happen. You want to call, the first function you want to call is going to be, well, get element. Because say, for example, I want to update lunar leaper, and I want to give it a throttle of 0.5 for its flow rate. Well, you have to call the get element function. You pass in a string lunar leaper. It returns that object back to you. So now you have the object in your hands. You can now reassign. You can call that object's change flow rate, pass in the throttle that you read in from the input, call its simulate function, and then what you can do is call the function update element. You pass in the same key lunar leaper, and you're going to pass in the updated object into the function. It will reassign that heap array's priority with this new object, this new lander object, and it's going to then either call bubble up or it's going to call bubble down. You got to figure out whether this priority value is bigger or smaller than the previous value, the previous priority that you had for this key element in the heap array. And then you just keep doing this over and over until all the landers have essentially crashed or landed. So what's going to happen, so I'll probably have to update the PDF actually, but the idea is as you're simulating, if at any point a lander has crashed or landed, you want to output that lander has either crashed with a sad face, or you output that lander has landed with a smiley face. And if that happens, you will then remove it from your priority queue because it will no longer be in the simulation. So once it lands or crashes, you remove it from the priority queue, and you simulate, and you keep just keep reading in the name of the lander with its throttle. You return that lander, update its flow rate, call it simulate, update. You just keep doing this again and again, and you output the top 3 every single time. This is going to be your main simulation, and eventually they will start crashing or landing. As you crash and land, you output your lander crashed, and you pop it off the queue completely, so you don't put it back in anymore. And that's the idea. And once you all have lander crash, your program is then finished. So again, the simulation is going to be very long. So I actually give you an input file that you have to use Linux redirection to actually read everything in. So I'm going to just simulate a few simulations here for you, but I will provide you with the actual input, or sorry, with the input and the output for the simulation as well. Let me go ahead and just simulate this for you right now. Okay, so this is the first file I gave you. So I had simulation 01, but ended up really not creating a very good output, so I discarded that. So I have sim 02, 3, 5, and 6 that came out to be rather good. So if you notice, there's a lot to actually simulate. So we don't want to constantly manually type these in, so we're going to use a redirection once again. So let me go ahead and just compile this first. So I have a main file. Then I have the PriorityQ file. Then I have the lander file. So you have to just compile, link all these together. So there it goes, it compiles. Then to run this, now once again, I could have run this the normal way. And right now we can see that it just outputs the top 3. And right now, this was in first place with a closest distance to the moon's surface. And these two are tied, but I believe in this case the other tiers actually, so maybe the fuel amount being smaller might give it the higher priority, but either way, these are top 3. And of course, I could type in gravity dodger 0.1. So I want to update gravity dodger and assign it with a new throttle 0.1 and update its velocity and altitude. So I actually have my program re-output this because, well, of course, like the same thing for previous assignments, you want to do that so you can see what the input was passed in. And notice, see, your gravity dodger now has a smaller velocity and has a smaller distance, so it updated accordingly in our queue. And of course, we can run through all of these. Again, of course, I can type in moon dance 0, and we can see that moon dance is actually not in our top 3 actually, because we still have gravity dodger, astro whoops, and moon mischief are still in our leaderboard. So okay, so let me go ahead and sort of end this for right now. So doing this is okay, but it's easier to simulate this instead by just, again, a.out, and pass in sim02.txt. It will pass all of these into our standard input C, and will read from this file. It's rather big. There it goes. Here's all the output. So the reason why I'm going to output what's read in, because remember when we do redirection, the problem is, as you can see right here, I asked the user enter lander name and throttle amount, and right here, normally I would go ahead and I would type in gravity dodger 0.1. Now I have my output. I set my output to just be fixed. So I would say just use IO_manip in your program and just do cout fixed. So that way outputs it in this kind of format, so hopefully there's no decimal round off errors. Hopefully, if I use a fixed, if there is, we'll of course have to manually update your grade on code grade for this. But anyway, the idea is that we output what was read in. So we have to cout that, because if you don't, this will be blank, and it's sort of hard to tell which input caused what output to occur. So you want to, of course, output these. And of course, our program reads this in. Let's go through and let's see if we find anything eventually crash. I think in this file everything crashes except for like a few doesn't crash, but it'll be a while to actually find those. I do provide you with this input file. Let me just go over here to output2.txt. Let me see if I can try to find. Let's sort of search for a smiley face. Oh, there we go. So this one landed successfully. So this one landed, so it's smiley face. So at some point, if something lands, you want to, of course, output that it landed. And when that happens, we're going to pop it off of the priority queue. We don't want to maintain this anymore, because now it's no longer part of our simulation. So then what happens is something else will be in first place. So whenever we have one of these things landed or crashed, we want to, of course, remove it. And of course, later on, we see here, gravity dodger has crashed. So I guess it didn't really dodge gravity, I guess, did it? That's a really terrible joke. So luckily the video is almost over pretty soon. So I'll have to, spend too much time after a very cringy joke right there. But you get the idea. So whenever something crashes or lands, we output the name, and then we output a smiley face or sad face. I'm trying to think. Did I make a mistake in my output because it doesn't have a space in between Astro Whoops and landed? So it might be a typo on my end, actually. So let's see. Well, anyway, if there is, I'll probably just fix that before I actually upload. So anyway, the idea is that all we're doing is one by one, we're reading in a name with a new throttle. We have to get that lander out of the queue by calling that get function, update throttle, simulate it, and then update and call the update function on the priority queue, which will, of course, bubble up or bubble down that lander. And we just keep doing this again and again. You can assume that the input will be valid, so all the landers exist, and they all will be in the priority queue whenever you read it. And so as we get towards the end, you notice that I update only a few landers, because at this point, most of the landers have already crashed or landed by now. So that's pretty much it. So anyway, also on a code grade, I also have some test cases that will test out your lander class. Also test out your PriorityQ class. And of course, there'll be a main that tests out your entire lander simulation main. So anyway, hopefully this video did help you. And I guess, happy coding, and until next time.